Good morning, guys. So here we go, part 2 of probability. Today we're going to look at tying in our counting principles, our counting methods, combinations, permutations, fundamental counting principle, to do some probability thing, and then bringing in something called binomial probability and exploring a little more with conditional probabilities. So let's look at these 3 examples I've got up here. Example 1. 2 cards are selected at random from a standard deck of 52 playing cards. What's the probability that both are hearts? Well, if we see in this, we could think of it as a dependent event scenario. The first draw is going to affect that second draw. So we could treat it as probability of 1 heart, then 1 more heart. No big deal. Okay, so probability of 1 heart would be 13 out of 52. Times the probability of a second heart is 12 out of 51, right? Probability of A times the probability of B given that A has already occurred. So we could go through, do the math on that. That's 1/4. 12 over 51 is 4/17. So when you combine them or multiply them, you get 1 over 17. So we can treat it like an independent event problem. Probability of A times B given that A has occurred. But what if we thought of it this way? What if I said the probability of 2 hearts, and we just treat it as a simple probability? Number of successes. Well, success would be any 2 hearts. Well, what are all the different ways I can get any 2 hearts? Well, that could be 13C2. Well, why would we use a C? And where does the 13 come from? Well, there's 13 hearts to choose from, and any grouping of 2 would be a success. So this is all the groupings of 2. Do we care which hearts we pull first? Does the order that we select those hearts matter? No, it doesn't. So since obviously we can't repeat hearts, I can't have the same heart show up twice in my hand. We know it's combination or permutation. And since the order we select those hearts in does not give us a different pair of hearts, a different countable group, we know it's a combination. So that's why we would do 13C2. And then our denominator would be all sets of 2 cards from the 52. So that would be 52, and would it be C or P? Okay, we know it's one or the other because we're not able to get the same card twice. There's no repeating of objects. But does the order that we select those cards in change what my 2 cards in my hand are? No, order does not matter, so it's a combination. So if we go through, do the arithmetic, 32C2 is 78. And 52C2 is 1326. And when you reduce that, you get 1 over 17. So as we can see, what is an independent event up here, because we have repetition to some degree of the same qualifier, we can look at it as a counting principle problem, or counting method problem. In this specific case, a combination. So it gives us an alternate way to be able to work that, maybe attack those a little bit different. I think these are a little bit cleaner and there's a lot more flexibility in there outside of finding all the little subtle nuances. All right, so that's one example. Let's look at example 2. Suppose the code to a lock consists of 3 different numbers from 1 to 99. What's the probability that the code consists of these numbers, 74, 42, and 26? Now, did it say those numbers in that order? No. It said we needed to have just those 3 numbers in there, so we could switch those numbers all around. Now, this gets a little tricky, getting that idea of a code. Is a code position specific? If I change the order of the values, do I get a different code? Well, the answer is yes. Can I repeat numbers within the code? Well, in this specific case, no, I can't repeat because I don't have the same number. And then it also says 3 different numbers. So that tells us we're dealing with no repetition. No repetition in our number of successes and no repetition in our number of possible outcomes. So we're into a combination or permutation problem. So the probability of getting those 3 numbers in any order is going to be number of successes. Well, a success would be all the orders of that. So it could be 74, 42, 26. That's one success. 74, 26, 42. That's another success. 42, 74, 26. There's a success. 42, 26, 74. There's a success. So we go through all the ways. Well, what's the way we can generate all the different orders of a group? Permutation. 3P3. We have 3 items, and I want all the different orders of those 3 items, because each order is a different code. So there's my number of successful outcomes. My number of possible outcomes is not focused on these 3 numbers, but all 99 numbers. So now we have 99 numbers put in all the different orders of 3. So 1, 2, 3 is a code. 3, 2, 1 is also a code. So even though they use the same numbers, when we change them up, we get a different code, a different countable object. That's what tells us we're doing permutation. So remember this, if we cannot repeat and the order gives us a different countable object, then it's a permutation. If we cannot repeat and the order does not give us a new countable object, we're dealing with a combination. And if we can repeat, none of the order stuff matters because it's just a fundamental counting principle. We just multiply our number of options together. So when we do the math here, 3P3 is 6, 99P3 is 941094. Just either remember your formulas from the other day when you were doing those. Just real quick, 3 factorial over 3 minus 3 factorial. So 3 times 2 times 1 over 0 factorial, so 6 over 0 factorial is 1. Okay, that's an interesting little thing that we need to be familiar with. 0 factorial equals 1, so that numerator equals 6. And then you do the same thing, 99, 98, 97 gives you this denominator. So when you do the math on it, you're going to get approximately 1, 2, 3, 4, 5 zeros and 6 4. If you want to make it a percentage, probably wouldn't be a bad idea. We'll just do 3 zeros and 64%. 2 decimals to the right to make it a percentage. Yeah. Okay. So there it is. If you want to leave it in this form, if you want to reduce the fraction by dividing everything by 2, it won't divide by 3. So we could just reduce the fraction. Decimal is probably a better indicator in this one of what's going on. So there's an example of how to use your permutations within just a regular probability problem. And then number 3. Suppose your bank assigns you a 4-digit PIN. Okay, personal identification number. Think to yourself, is it position specific? Yes, so we may be dealing with permutations, but let's keep going. For your bank card. The first digit cannot be 0, okay, there's a restriction on the first digit. What's the probability that your PIN uses the numbers 7, 4, 3, and 2? Now, number of successes for our numerator would be all the different pins that use 7, 4, 3, and 2. So very similar to this, all the different codes that use that, except now we have 4 objects that we're rearranging into all the different orders of 4. So 4P4 will give us 24. Let's hold on that. Give myself some room to do that denominator. Now the denominator would be all possible pins. Now I could sit here and say, okay, there's 10 digits to work with, right? And there's 4 slots to fill, so you would think maybe 10P4, but we have to ask ourselves, can we repeat items? That's first and foremost when we're deciding which of our 3 counting methods to use. Can I repeat items? Does it say 4 different digits? No, it just says 4 digits. You could have a 1, 0, 0, 0. Remember, the first number can't be 0. And that's a pin in this specific scenario. So because items can repeat, we don't care about order and all that other stuff for the denominator, which is the possible pins. We care about counting principles. So we have how many slots to fill? 4. There are 4 digits. How many options do we have for the first slot? Well, the first slot cannot be 0, so we only have 9 options for that first slot. How many options do we have for the second slot? Well, it can be any digit, so there's 10 options. The third slot, any digit, 10 options. Fourth slot, any digit, is 10 options. So as we go through, we already said 4P4 is 24. 9 times 10 times 10 is 9,000. So we can reduce the fraction, 1 over 375, or if we want to make it into a decimal or a percentage, that's also acceptable. So these are 3 examples of how we can take just regular theoretical probability, which we've been working with, and to take expected number of successful outcomes divided by expected number of total outcomes, and use our counting methods, our fundamental counting principle, our combinations, our permutations, to be able to get those number of successful outcomes and number of possible outcomes. Next, we're going to look at something that's got a, traditionally we use it for experimental probability. Every once in a while we'll get to throw some theoretical probability in there. But it's called binomial probability. So give me a second and I'll get that information up for you. Here we have binomial probability. Binomial meaning two terms. So binomial probability is the probability of an outcome occurring a specific number of times when only two outcomes are possible. Where the two terms come in is this idea that everything adds up to be 100%, especially, and if there's only two terms, then we have a binomial. X plus Y is going to happen a certain number of times. X plus Y is going to happen a certain number of times. And that's what we're going to be looking at. That's what we're going to be calculating. The probability of it happening that specific number of times. So the binomial probability, this formula we've got, is actually an extension of our binomial expansion formula that we worked with earlier on in the year. We'll explore that another day. But it's that idea, that's where they get that term binomial. Only two things are possible. Something's either going to happen or it's not going to happen. It's going to rain outside or it's going to not rain outside. We're not giving any gray area. Baseball player's either going to make contact with the ball or not make contact with the ball. Okay? And so it's a yes or no binary, ones and zeros, it happens or it doesn't happen type of scenario. And we're wanting to predict what's the likelihood that that will occur a specific number of times. And this is the formula that we use that for. Now, the way we say it is probability of R successes in N tries. That's not a dot, that's just the bad spot on my board. We'll do this. There we go. Probability of R successes in N tries. So we calculate that by doing NCR, number of successes, in all the different ways we can group those successes, the number of tries, in all the way we can put those tries into groups of success. And I'll explain more about that when we get into this, the problems here. And then we have x to the r, where x is the probability of success, y to the n minus r, where y is the probability of failure. So probability of success raised to successes, probability of failure raised to the number of failures. It's pretty straightforward. You just plug in numbers into a formula. So let's say we have a basketball player and he averages 70% on free throws. So when we set up our formula, we want exactly 4 out of 10. Well, that's what my formula calculates, exact number of successes. So exactly 4 out of 10 says we have 10 trials and we want 4 successes. Now what we're looking at here is the 10C4 is, did he make his first 4? Did he make 1, then miss 1, then make 1, then miss 1, then make 1, then miss 1, and so on? So the 10C4 calculates all the different ways he could have got 4 out of 10 correct. Don't care about the order, we just care that there were 4 out of those 10 correct. So that's what the 10C4 calculates. Now, go ahead and throw your probabilities in there. 70% probability of success means the probability of failure has to be the everything else. Complement comes in a little bit right there. So if we succeed 70% of the time, that means we fail 30% of the time. And then we put our numbers on there. I want to succeed 4 out of the 70 times, so then the rest of the time would be failures. So 4 out of the 10 times were successful, so the other 6 were failures. So number of successes with probability of success, number of failures with probability of failure. From there, it's just punching it, just doing your arithmetic, punching it in the calculator, figure out what your 10C4 is, and then multiply that times 0.7 to the 4th, 0.3 to the 6th, and work all that out. And we should get approximately 0.0368 or 3.68%. So that's really all there is to it, just recognizing the scenario that indicates we want to use this formula. So they're telling us the probability, and then they're wanting us to predict that event occurring a specific number of times in the future. So then we just plug in numbers into the formula. Now let's see if we had probability of at least 9 out of 10 outcomes. Now we know how to calculate an exact number of successes. This is a range of successes. Well, let's think about what happens. If it's at least 9 out of 10, that could be 9 or 10 successes, correct? Well, we know based on our last lecture that when we see the or, that's a union statement. That's telling me to add those two events together. Now they're not going to happen at the same time. They're mutually exclusive. I can't have exactly 9 and exactly 10 at the same time. So I'm going to figure out my probability of exactly 9, my probability of exactly 10, and I'm going to add those two together. So it's the probability of exactly 9 plus the probability of exactly 10. Well, how do we get exactly 9? Same way we did right here. 10C9 times 0.70 and 0.30. 0.70 occurred 9 times, successful 9 times. So that means we failed 1 time out of the 10. So we'll do that arithmetic plus same thing for 10. So 10C10, 70% success, 30% failure, succeed 10, fail 0. And when we add those two together, again, just punching it in the calculator, once you figured out what your 10C9 is, that one comes out to be, let's see, first one is 12.11%, then we have 2.82%, so the total between the two of them is 14.93%. Run out of room right there. Okay. Now lastly, what if we have probability of more than 1 out of 10? Well, let's think of what 1 out of 10 is. More than 1 means 2, or 3, or 4, all the way up to 10. So more than 1 out of 10 means all of those add together. So we would just repeat the process. Figure it out for 2, so 10C2, 0.7 to the 2, 0.3 to the 8, because 2 successes means 8 failures. Then we do it for 3, 10C3, 0.7 to the 3, 0.3 to the 7. If I have 3 successes, I have 7 failures, and so on. Now that can be very, very annoying to have to add up all 9 of those values. Let's work in the opposite direction. Let's use that idea that we looked at in the last lecture at the very end of complement. We know that all of these percentages together have to equal 100%. That's what the binomial expansion we were talking about earlier says, is no matter how I do all these, all these individual probabilities are going to add up to equal 100%. So why don't we just say 100% minus the probability that it's not more than 1, that it's maybe less than or equal to 1. Well, less than or equal to 1 consists of what? Probability of 1 and the probability of 0. So if we figure out what's not going to happen, we can subtract that from 100% and get the probability that it did happen. So let's look at our formula here. Myself some room to work. So the probability of exactly 1, I'll show you how I kind of get this organized if I was on paper, would be 10C1 times 0.7 and 0.3. I'll go ahead and do the probability of exactly 0. That's 10C0 of 0.7 and 0.3. And remember, those values don't change. 1 success means 9 failures. 0 successes mean 10 failures. So I can figure out what that is. So we punch all that in. We get 0.00014 0.000059. And we do all our calculations. And we just add it up. And this is going to give us the probability that we were less than or equal to 1. The probability that we were not more than 1. Now when you add that up, I don't know, what do you get? 1, 2, 3 zeros. My ability to add just left me. So 1, 2, 3 zeros, 1, 4, 5, 9. So it all comes out to be about 1.3 zeros and 1.5. Now this is the probability that he did not make more than 1. So that's probability he did not make more than 1. Let's just do 1 minus that, complement of all that. And so that would give us 0.99985. So as a percentage, that's a 99.985% likelihood that if he is a 70% free throw shooter, he's going to make more than 1 out of every 10 tries. So pretty sure bet, but again, there's always that small chance that's in it. All right, so this binomial probability is kind of allowing us to tie in a lot of the things that we've used prior to now, because we know the formula calculates an exact number of successes. And so if they give us an interval, more than, less than, at least, at most, those type of things, we know we're going to be using a union, figure out each of the individual number of successes and add them together. And potentially, if maybe there's fewer numbers that are not being asked for, we can calculate them and subtract them from 1 or from 100%. So a couple little options that we can use, that things we learned in that last lecture for. That's binomial probability. Again, it's just recognizing, are there 2 outcomes and only 2 outcomes possible? And am I trying to predict a specific number of successes to those 2 outcomes? Next, we're going to go and work with conditional probability a little bit more. So give me a second, I'll get that guy up here for you guys. Okay, so last thing I want to talk about with probability is conditional probability. Conditional probability we've explored a little bit with our mutually exclusive, let's try that again, dependent events. We had to look at conditional probability because it was probability of the first event times probability of the second event being affected by the first event. That was our how we calculated probability of dependent events. So again, it was probability of A and B, or A then B, same thing, was probability of A times the probability of B, given that A had already occurred. So we did the first probability times the second one, and the given that A means we adjusted this one based on whatever A happened to have done to it. Well, this formula that we have for conditional probability, all it is this formula just with the probability of A divided over there. So A and B, A then B, they're interchangeable. So we're not really going too much more in depth than that, but you'll see this. Now, this first problem I've got right here, notice how it's a whole ton of words. There's a little bit of space down here because it doesn't take any room to work. I hate this problem. I'm going to be honest with you. I do not care for this problem. I'm going to give it to you because you're going to be presented with it at some point. So I will go over this problem with you. And the reason you're presented with that problem is just so you have a reason to have to look at this formula, which is just this formula in modified version. The second problem I'm going to put up for you is where conditional probability is, and it's a more conceptual thing than a plug numbers into a formula thing. But let's go through this one first, get it out of the way so we can say we've covered it. A jar contains black and white marbles. 2 are chosen without replacement. The probability of selecting a black then a white is 0.34. The probability of selecting black on the first draw is 0.47. What's the probability of drawing a white on the second draw given that the first draw was black? So what are we asking? Probability of getting a white given that the first was black. Well, that sounds like a conditional probability. We have the condition. Well, if we look at our formula, probability of A then B, that would be probability of black then white should be divided by the probability of just A, which in this case is just the black. So it's just a matter of, there's B given A, so that's A, that's B, that's B. Plug it in, probability of black then white. Well, what they say, black then white is 0.34. Oh, 0.34. Probability of just black. Black on the first draw is 0.47. And so when you do the math on that, you get 0.72. So there you go. Probability of getting a white on your second draw, if your first one was black, it's 0.72. Look at that. We can plug numbers into a formula. Give me 1 second. I'm going to put this, forget it. I ain't even going to pause it. Let's just put it up there. This second one I like a whole lot better because it really gets into what conditional probability is. And it's the analysis based on conditions. So, if we have this information right here describing dominant hand, are you right-handed or are you left-handed? And we can break that information up into males and females. Say we did a sample of students around Riverdale High School, and we looked at some males, and 20 of them were right-handed, and 3 of them were left-handed. Okay? Looked at some females. 23 of them happened to be right-handed, and 4 of them were left-handed. What if I said, what's the probability of getting a left-handed student given that she's female? This is really what conditional probability is about. This idea right here. So I want the probability of getting a left-handed student given that she's female. I've identified a condition. What's the condition in this case? Female student. So I want to know the probability of getting a left-handed student if I'm only looking at female student. The condition eliminates everything else. We don't care anything about the males for this particular question because it said the condition of only look at the females. So we want the probability of getting a left-handed student out of the females. So how many left-handed students? It's just success over possible. 4 left-handed students out of how many females? So there were 27 total females. Now a common mistake people will do is they'll just go, 4 divided by 23. No, that's a ratio of left-handed to right-handed. That's not a ratio of left-handed to all students. That's not your probability of left-handed students to all, left-handed females to all females, which is what the condition is. Only look at that condition. So you go through and, that's it, 4 out of 27. This is conditional probability. This is what we should be focusing on. That other problem, you'll have some of those, plug numbers into the formula will make other people happy. But if you get this idea right here, that we're going to identify a specific condition, and now what we've done is our population, or our sample, our population is now fits only that condition. So our success over total is no longer all the left-handed students and all the right-handed students. And as soon as we said female, it's only females. Nobody else exists. All right, that's it for our second probability lecture. That's all the probability stuff we're going to do. I know there's a lot of stuff we crammed in here in 2 short lectures, but thank you for sticking through this, and I will see you in class tomorrow, guys.